Good morning.
Good
Um,
morning.
we
Good
actually,
afternoon, actually.
well, morning for me,
Good morning
afternoon
for
for
you.
you. Yeah. So we flipped the tables today. We're doing how we Linux first. We actually have a guest on the show today.
Me too.
It's been a long time coming. We've been waiting for him for like 9 years, 10 years. We've been waiting for him to come on the show. It's been so long. It's
That's what
been
he said.
so
He said the last time
long.
we
We've been
seen each
waiting
other
for
was
him.
maybe Amsterdam.
Yeah, we've been waiting. Well, before Amsterdam,
Well,
man.
me actually, I hadn't seen him since Amsterdam.
Yeah, you haven't seen him since Amsterdam, but we've been asking and asking for him for so long. I think I
So long, so
so
many years.
long. I'm
We
just
were
gonna
so
drag it
patient.
out.
We were so patient. We were so
I've been
patient.
wanting to have this show for quite some time. When I first started talking about quantum computing and engineering and everything around quantum, we finally got him. Uh, we're going to introduce ourselves, and then we're going to introduce the guy, the one and only Rick Nelson in the background. We're gonna introduce him, and then we'll also bring him up, and we'll have a conversation. So, oh, we got a commercial. We gotta do a word from our sponsor as well too.
You're
A
so
little show
hilarious with that one. A
rundown.
word. But welcome to Howie Linux. As you know, we if you notice, we switched the shows today. We're having Howie Linux first, just because we have such an awesome guest. I'm D. That which ways? That's Tamika.
And look, and down there, that's
And
Rick.
down there,
It's
that
Rick.
yeah
In
is
the
the doctor,
background is
the good
Rick.
doctor. Um, let's see what else. What else? What else? What
So
else?
a little background about today's show. We're gonna hit on some things that you normally don't hit on as far as quantum computing. Where is it going? What the history of it? Who is Dr. Rick Nelson? Why I chose? And then the other piece of this is we want to leave questions up to you as well too for you to ask your questions. Right? This is no time like the present. Like I always say, be ready for whatever, right? And if you all have questions and you want to know, you may be interested into how could your son or your daughter or you yourself get into a career field or a research field as this, and go from there. I just want to put information out there so you all can see where not only, and this is gets back into the whole DevSecOps, because IBM has a quantum computer and they hiring DevSecOps engineer to deploy to their quantum computer, but it goes to show you how everything touches each other, right? How you could be a DevOps engineer and deploy application to a quantum computer and know nothing about it, or you could be a researcher and know nothing about DevOps, or you could be a cybersecurity person that does research and never ever deployed an application before in your life or secured one. It's just so many different things that you could get into as far as tech goes and where it expands to. All right, D.
So get your notebooks, get your notes, get your other screen ready so that you can Google some of these terms that he's going to be using. I know he's not going to talk over your head because that's just not the type of person he is, but he might geek out because that's what we do. So now a word from our sponsor.
Hey, everybody. Welcome to Women in Linux. I am Tam, and D is in the background. And we just want to share with you some of the perks of being here on our channel. All right. So, first things first, if you want to connect with us on social media, connect with us anywhere on social media at Women in Linux. If that's just too much for you, you can always come and find us on womeninlinux.org. And if that's not enough, we have even more perks where you can hit the connect button. Once you hit connect button, you put your email address in here, and once you put your email address in here, it'll connect with us in our Slack group. We have tons of resources in our Slack group. People looking for jobs, people just looking for advice, people looking for information, and so forth. Right. So again, this is Slack. It's not Discord. So on with using Slack, warn you, it is resource heavy. So you may need to use either the web browser, or if you're on your phone, you should be fine. But if you're on your desktop, and we know most of you connect on your computer, it's easier to open it up in your web browser so it doesn't take up so much memory or so many processes and so forth. That's just an FYI. That's how I use it. Okay. And if you would like to shop with us, we still have our stuff from our 5 year stuff. Still good. We're working on more T-shirts. No, no estate, no date. We're still working on that. But again, if you want to shop and you want to get some merch, feel free to come here and get some merch. Again, if you come over here and click on all products, you'll see on all the products that we have, from hoodies to masks and so forth and so on. Right. And if that isn't good enough for you, you can donate. You can always donate with your time. You can donate with your money. So, how do you donate with your time? You donate with your time by saying, "Hey, I would like to do a presentation, or I like to volunteer on helping us grow the channel." You retweet, you share this with other members. In fact, for those of you that come here every single week, we know you come here every single week and you don't subscribe, subscribe. That helps us grow the channel. That helps us get more content to you. Hey, research isn't easy. I'm not getting paid to do research. I wish it was at a university, but hey, I'm bringing this to you, right? I'm bringing this to you and us and for others, right? So if that doesn't work, you can always donate on PayPal by clicking the donate button. Once you hit the donate button, you have your own denominations in which you can donate. And if that doesn't work to you, for you can always reach out to D and you can cut a check and send a check. That works for us as well. All right. So, what are some other things that we actually do have as well? Right. So, we have a discount with IT Pro TV. You get 30% off. I've used IT Pro TV myself. I've done interviews with them. I'll pull those up as well too. But as you can see, I'm logging into IT Pro TV. What are the benefits here? You need to learn how you learn. So, one of the things you can do in IT Pro TV, you can come over here, you can click on courses, and it gives you a list of courses that's separating them out by certification, and also separate them out by learning paths. You're like, Tamika, what does that mean? My four basic principles, or my four basic foundations of skill sets that you should have is Linux. You should also have an automation tool, whether it's Terraform or Ansible. You should know at least a cloud. I don't care. Pick either one. And finally, last but not least, security. And security comes in multiple forms: security of the operating system, security of the application, and also security of containers, right? And cloud security. So it's multiple facets when we're talking about security. Those are your four basics that you're going to need to to get you a job and then move you up. All right. And we're going to talk about our membership here in another video, but I just want to get this out to you. All right. So that's 30% off of IT Pro TV. And last but not least, our Calendly. We have set up for our Calendly. Let me pull that up. I think I have it saved in my browser here, so I can just go straight to it. If not, I'll get it from D here. Here we go, right here. All right. So with Calendly, we have one-on-one sessions. That's where you get to talk to either me or D, and you can request either one. But where you get to talk to us in a one-on-one session, right? Interview prep. Some of you are getting ready for interviews, or you never interviewed before. We want to prep you for an interview. Resume review. Let's go over what you have, or let's pull all your skills together. Let's get things formatted properly. Let's get everything going. And last but not least, career assessment. What is your journey? What could it look like? What could you be going through? What are your next steps? Some of you are transitioning, some of you are not, some of you are looking to transition, and some of you are just trying to figure out what is your next step. So by saying all of this, we want you to enjoy your time here at Women in Linux. And also, as always, don't forget to like, subscribe, hit the share button, and last but not least, thank yourself that you actually did it. We're back.
How awesome was that?
Miss
Our
Phoenix,
sponsors.
word from my sponsor. Miss Phoenix, thank you for the $30 super chat. D, thank you yesterday for enlightening resume review and
It
stuff.
was awesome. It was awesome. I'm looking forward to your plan. Looking forward to it.
I went through and gave some pointers there. I hope y'all had a good time on that resume review. Again, we try to give a 360 view here. All right, no, with no delay, because I know he's back there patiently waiting. We're gonna bring up Mr. Dr.
Doctor.
Richard Rick Nelson.
Hey Dee, hey Tamika, good to see you guys.
How you
Great to see
doing?
you, Rick.
I'm doing all right. It's been a while. Thanks for
I
having
know,
me on the
right?
show.
I know. We had a word from our sponsor. We had to go through all our things and
Of
get
course. Yeah.
all that out there. But today the light is shining bright on you. Uh,
Awesome.
we are going to get into it. So, uh, Dee, is there anything you want to say before we get into it? Before we start asking Rick
I'm
questions?
just as excited about the audience, like the audience. I'm like, what are we going to talk about? Which way is it going?
Yeah.
I'm queued up. I'm ready to like drop down and listen.
Awesome.
Me and Rick already had our chat in the back before we came up, so
I
I'm
Yeah.
got you.
ready.
I got you.
Practically don't even need to be here. Dee's an expert now on quantum computing. Oh, so-
Talk to us. Talk to. I'm not. I'm ready. I'm ready. I need to know. I need to know what's going on.
Okay,
awesome.
cool. So let's get started. So Rick, let's go with you want to. Let's start with this. Let's start with how we met. It's the
Oh, yeah, sure. So
easiest part to start with.
well,
So go
yeah,
ahead.
go ahead. No, you
No,
go
no, go
ahead.
ahead.
You could. Okay. Well, I think we met first over the phone because I called you.
Yep.
I have a small business that I run that helps do IT support for the Department of Defense, and I gave Tamika a call one day and said we've got a brand new project in DevSecOps, and we need an expert in infrastructure and HashiCorp tools and all of that kind of stuff. And Tamika said, "Yeah, I can do all of that stuff," and she can and did, and came on and has been working with our company, Expansia's my company. Can we say that? Can I say that on your broadcast? Yeah,
Yeah, yeah,
right.
yeah,
Yeah,
yeah, yeah, yeah.
that's cool.
They know
And
about you
since
all.
since since then, I've been following.
You went on mute. You went on mute. We can't hear you. You said since then you went on something. Still can't hear you. Oh. Did it die? Yeah, it might have died on you, Rick. It doesn't have a quantum battery in it, so it's probably dead. And no here, over here. Uh-oh. Rick has got to troubleshoot the issue live. No pressure. No, still don't hear anything. You're unmuted, but I don't hear anything. What's going on, Stacy G? It's all good. You want to come? We could drop you down until you get your sound fixed. Oh god. No, you muted. Now try unmute. Can you call Tech? We need help desk here. You still muted on your end though on the thing, so unmute on StreamYard. I don't know why it just clicked off, and I don't think I can unmute you. Let me see. Yeah, I can't unmute you. You have to unmute yourself. Uh-oh. Yeah, we can't hear you. So what D can do, we can pull you down in the background and then we'll we'll bring you back up. I can get a story, it's no big deal. All right, so D, you can pull him down and then we'll pull him back up. All right. So Rick, we still here for you. So long story short, so he called and we ended up talking about deaths at cops and what the DoD was looking for, so forth and so on. Ended up talking to Chad, and I actually forget Chad's last name right now. So in the
I'm gonna bring him back up to see if he can hear. He's unmuted himself.
All right, can you hear me now? Can we hear me now?
Yes.
yes, what happened, Rick?
Taking the headphones off.
Okay, all right. So
All right,
we
I'm
met.
back.
You called
I
from
can't
the
hear you
Springs.
though.
Uh oh.
That's the problem. I can hear D. I can't hear you, Tamika. I'm sorry.
Oh, what?
You're
You
not
can't
on
hear
mute.
me? So you still can't hear me?
I don't know how that happened.
Can y'all hear me in the chat?
It didn't. Do
I
it.
can hear you.
I can
Okay.
hear you, D. I can hear you just fine. I just can't get
What browser are you in?
Chrome.
Okay.
No,
Yeah.
chat. Type in a
You
one. Type a
mentioned
one in the
DOD
chat.
and
Y'all
it went
can get
left
up.
from there.
What'd you say?
That's it. You know what? They're probably listening in, and they just cut the feed.
Yes,
Right?
Rick. Yes. You know how I feel about the man.
The
Yes.
NSA listening in, or one of the 3-letter agencies.
Yes. You see what happened? And Donald said he can hear all of us, so I don't know. So
So
I could hear.
D, you could
I
take
could hear
you
D
could
just
take
fine.
you
I
could
just
take
can't
the
hear
lead.
Tamika at all.
no,
I hear you.
so Rick, do you have another screen? I suggested you have another screen up with YouTube. Can you?
No, it'll be an echo.
I know,
No,
but I'm just saying. I just want him to test it.
That was one of the things I canceled when I
Oh
go
yeah,
to it right
D
now.
D just take over. Just remove.
Well, you're not alone. And when it
Well, I don't know what the question's gonna be.
D just take over. Just remove.
well, you're not alone. And when it
It's all good. You can
Well, I
just
don't know what the
remove
Okay,
remove
Tamika,
me. I can
just
take over. Just remove.
well, you're not alone. And when it
It's all good. You can
Well, I
just
don't know what the
remove
question is.
remove me. I can take
well,
over. Just remove.
you're not alone. And when it
All good. You can remove. I can take over.
Hold on, I want to get it. Rick, what I'm gonna do is I'm gonna kick you from the stream and you come back in because you should have audio of everybody. Can you hear me now?
I can hear you. I can hear you. You're going to kick me
Okay.
out. You're going to come back in.
Yeah, I'm gonna kick you down and you're gonna come back in.
All right. Do I have to do anything?
No, you just have to. I'm gonna kick you out and you just use the link to come back in.
The YouTube link?
No, the link that was in your invite.
Oh, the link that was in the invite. Okay, hold on a second. Okay. I'm ready.
Okay.
Like Dub, you funny. Just restart the PC at this point. You funny.
Hey, I'm gonna kick you out. You're gonna come back in. I know Tamika, she asked all the good questions. I'm in here like a deer in headlights. I'm still drinking tea.
It'll be okay. You would just have regular questions. We gotta bring him up. Hold on. All right, Rick, can you hear me?
I can. Yes, success.
Can you hear D?
When in doubt,
I can
kick
hear
you
D.
out.
I can hear you guys. Well, that was, that's the way technology goes. And I got good news and bad news in the field of quantum computing. They've come a long way in 30 years, but we're still a little ways away from having a commercially available. Anybody can go buy one quantum computer. So it's kind of like this technology here.
But I like people to see things in real time to let people know we have real problems and anything can happen. Yep. And this is how you troubleshoot and work through it. So this is perfect. Everything happens for a reason.
Cool. All right. Well, let's get going so I don't shortchange your
audience. Yep. So basically, you called. We got hired. We did work, and we still do work. Together here and there. Right. And now we're gonna talk about you. All right. So you chose. Why did you choose get your PhD in quantum? Was it quantum physics or quantum engineering?
I would call it quantum engineering. It actually was a hybrid. Didn't start out as quantum engineering. I started off studying control systems. The dissertation was actually geometric control of non-holonomic classical and quantum mechanical systems.
And that means what?
Yeah, it's a good question. So I started off with the idea that you could control certain systems that are non-holonomic, which I know is a big fancy word, and you didn't have to even remember that word. But it just means that there are certain constraints on the state equation, certain ways that you can't move the physical system, but you still want to get your system to a place where you want to go. Simple explanation would be you want to parallel park a car. Your car doesn't go directly sideways. So you pull up next to a parking spot, between two other cars that are parked at the curb. You want to get your car in, but it doesn't go directly sideways. But you can pull up a little further and turn your wheels and back in and go forward and back and forward and back, and you can get yourself into a parking spot. That system is a non-holonomic system in that it's got this constraint. You can't go sideways, but you still want to control the car to go sideways. And you can make it go sideways, like little back and forth motions where you turn the wheel like crazy and go a little forward and back. That's a non-holonomic system. And I was looking at how to control satellites and how to control their attitude, which is the way they're pointing in space. And one way that they do that is they use something they call a control moment gyroscope. And gyroscope is just a little spinning thing. It spins. And if you put a little torque on that spinning thing, kind of like leaning when you're riding a bicycle or a motorcycle, and I think, Timothy, you know all about that. But you put some torque on it, and it applies a force or rotational force to the platform, and you can get that satellite to rotate in various ways. And I was doing some work on what happens if some of those gyroscopes go out. Can I still get the satellite to orient the way that we want it to? And under certain conditions, you can. It ends up being a very mathematical thing. But I was trying to derive the control inputs to get the satellite to move where I want it to go. And along the way, I was thinking, it'd be great to actually try this out instead of just doing a bunch of simulations. But NASA didn't have any satellites. They wanted to just let me try for fun. So I started looking around for other systems. And then somebody said, I think it was one of my people on my dissertation committee said, spins on gyroscopes kind of look like spins on nuclei. And you could use nuclear magnetic resonance to do instead of a big satellite. Now I'm talking about little microscopic things, on the order of angstroms and nanometers, where they're little spins. You could control those systems. And then that led to what will we do with it? And can you control them? And quantum computation is all about controlling spins. Spin 1/2 systems is the basis for quantum computation. And some of the things that I found in my research had implications for quantum computing. So that's how I got into it.
Now, I know the audience is like, what in the world are we doing?
That's the most technical part. I won't get that technical for the rest of the.
It's all good. I want you to be technical. We are technical over here. We encourage taking notes and pushing out definitions and going to look them up. Don't hold back being technical over here for the sake of losing the audience. It's okay.
Okay.
It's all right. So now you chose that as your major. Looking out over the landscape from your major then until now, what have you seen in the quantum realm? I can tell you what I've seen. I sent you some links this morning, but what have you seen from your perspective? Like what gets you excited about the field now?
Well, one of the things that's exciting about the field is it's still got a lot to learn. We're still a long way away from, we're closer, but we're still a long way away from solving all of the problems that would be needed for a really viable quantum computer. Just recently, like within the last couple of years, IBM did an experiment that they published in Nature that does something they call, quantum supremacy. The idea that you solved a problem using a quantum computer faster than theoretically possible on a classical computer, the kind of computer that sits on our desktop, or even a supercomputer that uses just classical bits. There's some controversy over even that, though, is to say, well, did they really show quantum supremacy to the level that it would be, viable yet? When I was a student, we were talking about demonstrating things with a 2 or a 3 or a 5 or a 7 qubit system, right? In fact, the experiments I did were 3 qubit systems. We're trying to just demonstrate that you could generate an XOR gate or an AND gate. You're a NOT gate with, the idea is how do you build those things and show that you can do them with a 3-qubit system, let alone computer, right? You can simulate with a classical computer everything that a 3-qubit system could do, in a few milliseconds. The 3 qubits isn't going to buy you any earth-shattering speed up in computation for anything, So what I show, I can factor, 6 into 2 and 3 a little bit faster than you could do it on a classical computer. Nobody's going to pay attention to that. You got to show you can factor, say, 128-digit number, into its 2 prime factors. That, then you're starting to show that quantum computation can rival or even beat now best what a classical computer can do. And then, so when you start to get to that realm, then you're starting to say, yeah, it can do something that will perk up and grab our attention. We're not quite there yet, but we're closer than we were obviously 20, 25 years ago when I was working full time on this as a graduate student. But seeing the advances has been kind of neat. You've seen back then, the way to simulate a quantum computer was to use, they only had a handful of ways to do it. A Bose-Einstein condensate and the advances that brought in trying to use trapped ions and that kind of thing were brand new idea in the 1990s. Using nuclear magnetic resonance to simulate a quantum computer because you have this readily available spin 1/2 system, even though you're doing it in the aggregate, that was a fairly new, readily available application. But a lot of the ways they do it today, back then, they still hadn't figured out how to use photons for quantum computation. Now they do it all the time. So seeing these new ways, you got quantum dots, you got quantum superconducting loops, Cooper pair squid ideas on how to create a lattice of quantum bits. Those are all advances that we've seen to the point where they can build a quantum computer now with a few hundred qubits. Of course, they need to get to several thousand before we're able to solve the real hard problems. And they've got roadmaps that show they're going to get there in the next few years. It's going to be exciting.
Now, I've been following quantum now for a while, and everybody is on this race in cybersecurity to crack the AES 256 bit, right?
That's right.
Everybody's on this roadmap to crack this, and they're like, once this gets cracked, everything in the world is going to shut down, right? It's over for the world. And that's been this talk for like about 3-4 years now. Every time it comes up, the quantum computing is much closer to cracking the AES 256 bit. It's very close. What are we going to do? How are we going to solve this? So, Rick, are we really that close?
I don't think so. I think we still got a ways to go. They've demonstrated for one, but who's got the time to go do that for your bank account? And not only that, but while people are working on implementing, and what we're talking about here for your audience too is in the early 1990s when the idea of a quantum computer was first posited, that it might be useful for something. The question is what would it be good for? What would you use it for? What would it, rival classical computers to do? And a research scientist at IBM by the name of Peter Shor came up with an algorithm that you could factor, numbers instead of having to try every factor up to the square root of the number you're trying to find the factor for in order to verify, what the factors might be or to verify that it's a prime in the first place. He showed how you could do it, much faster, right? So instead of a 2 to the n problem, you're talking about something on the order of n, some factor of n. So it's more of a linear problem instead of an exponential problem. Now people start to perk up. And since that's the basis for your RSA security and all that sort of thing, people have been worried about cracking this RSA security ever since quantum computers and Peter Shor's algorithm showed up on the scene. But people, while they're working on cracking that algorithm to make up, people are also working on how to use quantum cryptography to encode. And, while we can use quantum computation to crack a classical encoding algorithm for keeping our stuff safe, if we use a quantum computer to do that, why don't we use quantum information to encode now our transactions and our bank accounts and that sort of thing, which a quantum computer would have a hard time cracking. We'd have to come up with some new, more advanced scheme, perhaps, in order to make that happen. So while we're working on ways to defeat current RSA, we're also working on ways to substitute something even better for it that would be safe using even with a quantum computer on scene.
Now I did. Thank you for answering that. I also do have. Let me share my screen here. Hopefully, I can share my screen. Let me see. Hopefully, it don't act up. I may not be able to do it because I had to undo some stuff last week. Cool. All right. So this one right here. This I know this is kind of dear to your heart right here. NASA's JPL uses Microsoft Azure Quantum to manage communication with space missions. So
Right.
you're right. So I was looking at that this morning, then thinking about what you were just saying, and I've been seeing a lot of this. Right, I've been seeing a lot of startups come out, and a lot of VCs, venture capitalists, invest in these startups for blockchain in space and
Mm,
quantum in space. Now, with quantum in space, I don't know what that looks like, right?
mm.
What does that actually look like, or what do you think it looks like? You may not know, or you may have an idea, but what does that look like? We're talking about quantum in space. What are we actually doing with quantum in space and satellites? If you're at liberty to say, if you're
Yeah. Well, there are a couple of things that come to mind right off the bat. First of all, just we talk about how an architecture of a quantum computer gets put together. Right now, one of the main ways to do that is to use superconducting devices, tiny little loops, and the direction the current goes in the loop tells you whether it's a 1 or a 0, and then you can have a superposition of 1 or 0, which is what we call a qubit. Right, it can be a
Mhm.
1 or a 0 like a classical, or it can be in a superposition of those two. That requires very cold temperature. So one thing that would help you is if you're running the computer in space, is it would be less expensive to run it there. But I think what this article was talking about, the one you have here, it's
Mhm.
applications of quantum computing that would help with space, and that is a scheduling problem. This
Okay.
is how do I schedule resources? And you can think about, well, the end all be all of problems to solve. One of the end all be all problems is what we call the NP complete problem. It's one of the hardest problems that our mathematics topology will say to solve. And one example of an NP, a non-polynomial time problem that it would take to solve on a computer is the classical traveling salesman problem. And
Mhm.
some proofs out there that show that if you can solve that, you can solve any NP complete problem. They're all equivalent. And this is a really hard problem. NP complete problems are actually too hard to solve on a classical computer. They actually happen to be too hard to solve on a quantum computer as well. But the quantum computer can do some things to help with scheduling to optimize things. And this is why one of the applications for which a quantum computer would be good.
Mm.
Optimization. So
Yeah,
optimization,
right here.
yeah. So optimization for scheduling and for resources. You got a limited number of sources. Maybe you got 1 million people trying to use the satellite all at once and you've got only a limited bandwidth, and you don't want to interrupt your communication mid-packet and that sort of thing. So scheduling how to optimize the satellite, because to put a satellite in space costs a couple $100,000 per pound. So it costs a lot of money to put a satellite up. So it's starting to cost less, but still, you want to optimize those resources in space. One of the problems that quantum computation could help do is to optimize the communications channel. So you're squeezing every last bit out of it.
Right. And here it says, when you're talking about optimization complex, optimization problems exist across every industry, such as vehicle routing,
Yeah.
supply chain management, portfolio optimization. I'm assuming they're talking about your finances when we're talking about that, right?
Yeah, that's right. I mean, you want to model the stock market and stuff like that. It's like a day delay now in order really to get You can't get up to the second models to predict what's going to happen with everything. You can get some for, in mid-range, or a few things change here or there, and I know what to do immediately. But some of these, you got to wait for a few hours for you to run a complex model of financial markets. Quantum computation could speed that up by maybe a factor of 1,000. So I could get instant information about what to do based on, the inputs.
Now, with that being said, you may not know this. That with the Monte Cristo,
Monte Carlo.
Monte Carlo, is that with the Monte Carlo when we're talking about this model? When we're
Yeah, it's better than Monte Carlo. So it's a competitor, if you will. So in a what happens with a classical computer, any computer, I think about the computer is, I have a bunch of inputs. I set up a state that is the bits. Maybe it's you initialize everything to 0 or whatever. You set up your initial state, right? And then you've got some function that creates the model for what you're trying to find the answer to, and it allows those bits to evolve, jump back and forth, or flip, or whatever they need to get to the answer you're looking for. And then at some point you get an output. Well, in a classical computer, you've got to look at every one of those sequentially. You've got to look at every possible input. So maybe I start with the Monte Carlo methods is I got to have all of these inputs with these frequencies, this probability that all of these things are going to happen. And I look at a whole bunch of stuff in aggregate. And the only way to look at a whole bunch of stuff is I put a set of inputs in, I see what the answer is, I write it down. I reset everything. I put a set of inputs in. I run it through my algorithm, and I write that answer down. And I do that like a zillion times. And then you take an average at the end of all of those runs. But I still had to make that run and reset the computer to its initial state, and then run it through again a whole bunch of times, and then average at the end. Where the quantum computer, you do all the runs at the same time. You set up the initial state so that it's a superposition of every possible state.
Gotcha.
And then you do one time, and then when you measure a quantum computer at the end, it is the probabilistic answer. So it's like running Monte Carlo with a single step instead of a zillion steps, and then take the average at the end. It does the averaging for you, if you will.
Oh, that's even better, because what I find is because when I talk to a lot of the financial advisors or looking at them on YouTube, they all run the Monte Carlo, and I'm sure there are other algorithms to run. And I'm like, man, like they're always giving like, what's the best scenario for you to withdraw this 3%, 4%, 5%? At what age should you do it? And again, those inputs is what Social Security, when should you take Social Security, when should you not? What's going to be your RMD, required minimum distribution, to pull down, and then go from there, right? That's normally what I've seen. But from what it sounds like, the faster we can get there, maybe the portfolio, or your financial portfolio, would be a lot healthier sooner, because you've ran these different, I guess, inputs or different situations for someone. And then instead of me, I wouldn't say instead of me waiting, I would say instead of this person putting in all these different inputs, because usually it takes a while for the advisors to get back to you. It usually takes like about a week for them to get back to you on a decision. And you're like, well, what are they doing? Number one, and two, should I be talking to somebody else? Or do you know what you're doing or whatnot? That's usually what I've seen is a week. But that's just my take on it.
Right, and all the inputs that you just mentioned, like how old and that kind of stuff, that's just a handful, and those are your personal inputs. But this would be looking at what is the current price of rice in Beijing in the certain market today, could influence the whole market stuff, right? What about what it would take into account things like the current status of the fowl market in Southeast Asia, where is there another disease coming out of there? It might take into account weather patterns that might disrupt farmers in Patagonia. It may have an effect on the market in the United States. It'll take into account, the price of pork barrels and all of its past history and where we are today. You can model all of that stuff to say, here's how to optimize Tamika's portfolio. But it takes into you want to model the real financial market. You might have a million inputs. You can't model that today with the current computers. It just takes too long. By the time you got the model out, like you say, in a week, they had to dumb that down because the markets have all changed. So by the time you get the model out,
Yeah, we've gone. A week is too late. That's what it looked like last week, and this is what we got to go with because it takes too long.
So there you go. Optimization problem in financial markets, even weather modeling. When I actually first started in quantum computing in my degree, that's what we were looking at doing. In fact, I was using a 3-qubit quantum computer and showing you could do some gates in anticipation of modeling the weather someday, to be able to take all of the pressure and the wind and the temperature readings and all of that stuff from around the world, and whether a volcano went off over in some southeast Pacific island and all of that kind of stuff, to predict what the weather is today. Because today, the models they run, they have big fancy computers to run those models, and then they'll only tell you it's 70% chance of rain. Why is it only 70%? Why can't they tell me when and where it's going to rain with 100% accuracy? Well, it's because their computer models are limited into how fast they can run and the number of inputs that they can handle, the number of states they can run through, and the Monte Carlo simulations they can run. And it's limited by classical computation. So if you had a quantum computer, we might know now, hey, it's going to rain at 3:42 today, so I need to be home by 3:41 so that I'm not caught in the rain. I mean, that's the kind of thing we're talking about.
Gotcha. Now I'm gonna ask a silly question, and you may or may not know. Who is Monte Carlo?
Who is Monte Carlo?
Yeah.
Not a person. It's a city-state in Europe where.
Right, but why is it named the Monte Carlo for the for when we want to do modeling? Where does that come from?
My guess, I don't know for sure. My guess is I've always thought it's because that's a city-state in Europe where gambling is a big deal. People go to Monte Carlo to gamble, so it's like a probability thing. It's like rolling dice in a computer. We're just going to roll the dice and see what the possible solutions are. And if I roll, a box cars, then I do this, and if I roll snake eyes, I do that, and I do it over and over again and see what the average is.
I was just always curious. I never really looked it up why they called it the Monte Carlo, but I just was curious as why they called it the Monte Carlo. Like, where does that name come from as to why we want to name that simulation that?
Yeah, it's all probability, I think. Do you want to go all in on the need to draw an insight straight on the river? It's all that kind of stuff.
I think you did have a question in the audience. That is the question I wanted to ask, dealing with numerous variables that's so dynamic to change how quantum computer will handle it. And engineering cannabis, you asked what were the questions. The questions are in my head as from based on the links from that I sent Rick, and what I know about quantum computing and where that's going. So that's what it is. That's where it's at. It's no specified. We're free flowing on this conversation to understand quantum computing and so forth. Now, I know you mentioned IBM earlier. I know Honeywell has a quantum computer. Microsoft, Google has one, and
Amazon
there's
probably is working on one. I can't imagine they're not. Yeah.
right, and everybody is working on having a quantum computer. And I know Amazon offers quantum services now. On
Azure.
Yep, and so when you're looking at these, do you think they're true quantum services that they're offering, or do you think there's some type of simulation? Are we actually deploying applications to this quantum computer?
Well, not applications in the sense that we usually think of them. Most of the things that we're doing and actually you can, as just a normal, ordinary citizen, request time at on the IBM quantum computer to run an experiment, but it's not going to be a regular application. A couple of things to know about that. First of all, the quantum computers are probably only going to run for a second or two. So your experiment's not going to be very long. You're not going to run it super long. And one of the reasons is because the hardest part about creating a quantum computer, probably the hardest part, is you need to have all of your qubits be able to interact with each other, but nothing else. So you set your system up, you set it up very carefully to get all the qubits the way you want in your initial state, kind of like, setting all your bits to zero, it's initialization. But you set your qubits all up in your initial state. Usually you want that to be in a maximally entangled, highly correlated state, of all of these qubits, which means they have to interact with each other. But if they interact with the environment and how you're going to hold these qubits so that they don't, but they interact with the environment, then they start coupling with the environment. The environment messes the state up. It introduces errors, and any amount of heat that couples with this quantum computer, it decoheres. We call it decoherence. It makes the quantum states collapse. It's essentially a measurement. That's what you use the environment to do, to measure stuff. So basically, you want the environment to have all kinds of connection at the beginning of your setting things up. And then somehow you don't want that quantum computer now to touch anything and to be completely isolated and be at absolute zero and nothing touch it until it's run through all of its computations. And then you want to get in and measure it. And you have all kinds of access, but you have to do it at the right time and so forth. And that's hard to do. It's hard to isolate this stuff, even if they're photons or whether they're little quantum circuits or whatever it might be. Trying to get them to not touch anything, not be available for the environment to interact with, is tough. And so typically your quantum computation itself right now really only lasts, on the order of a couple of seconds at most before everything goes haywire. And you have to make your measurement and hope that it's good enough. So that's one of the issues that we have. And now I can't remember why I started talking about that, but it is important. What was your question again? It was.
I actually forgot just that quick, because I had another question in my head. Well, another thought in my head, because Mercedes Benz uses quantum computing, I guess quantum optimization for their batteries, because the EQS to optimize how the range in which the battery can last and actually work.
Well, let's be fair. They're not using it yet, right? So here's the idea: is to design a better battery, you got to model what's happening at the physics level with all the possible chemicals and their chemical reactions that are required in order to create a battery. And classical computers have a hard time with all the possibilities. Again, the number of inputs, the number of possible inputs, and the number of interactions that could and do happen. It's hard to model. In fact, modeling is one of the best reasons to build a quantum computer, is because we need to be able to model these sort of things if we want to make advances, because classical computers can't do it. They just don't have, the speed or the bits in order to have it happen. So a quantum computer can take, a million, ideally you got 1 million qubits. You can model the crap out of this thing, and you can find out then, hey, if I add this much lithium and this much sulfur and this much, and I put it in this arrangement, and I had the crystal structure just so, then my battery is 20% better than the lithium batteries of today. And that's what they're trying to do at Dalmer and at other places too. They're trying to design better batteries, but that's, again, it's a simulation of nature that we're trying to get a quantum computer to do. Oh, and I remember our former question now too, which had to do with how does what experiments can we do on these quantum computers? So some of the experiments are, you might have a novel set of gates. You don't program a quantum computer like we program classical computers. Right now, it's all at the say, the AND and XOR and OR gate level, and how do I program that, and how do I and what results do I get? So really, experiments are kind of on this level of, if I have 100 qubits, what sort of answers can I get? Maybe you're trying to show that you figured out an algorithm, a way to program with those kind of qubit gates, how to do a factoring problem. Or maybe you're trying to model some simple physical process with it, just like you would with a classical computer, except the classical computer, you have all these tools, right? When you go to program a classical computer, you don't have to think about assembly language anymore. You've got higher level languages that take care of the assembly language stuff. And we're even before assembly language. We don't even have a language for quantum computing that's at that level yet. The assembly language takes care of all of the gates. It takes care of all your anding, your or, and your twos complements, and all that kind of stuff. We got to figure out how to do that now with quantum computers. So the experiments that you're running is just to see what it can do, and fulfill your own hypotheses, experiments on your own hypotheses about how quantum computer might work and how it might be better or faster than what you might do in the future. And all of that is research. So what do we use quantum computers for right now? What do you do at the IBM thing? It's research stuff. You're not trying to model your portfolio yet, or Wall Street or battery chemistry yet.
Got you. You did have a question, says, with predictive algorithms, especially with GDP, how can quantum computers handle unknown variables?
Same with you would do with a classical computer. You have to generate a model. You have to put probable numbers on those. Use Monte Carlo to decide what the probabilities ought to be, and you run your simulation. It will be the same. That would be the same idea. The advantage of the quantum computer over the classical computer, again, is your ability to run multiple simulations at the same time. But I mean, the idea is you would have to model it a similar way. You're trying to get some answer out of your computer, which requires an input and some kind of state evolution, and then measurement at the end. And it's no different between that or a quantum computer. Just the quantum computer uses a different way of doing it.
Now, I know we've been talking about qubits this whole time. We've never said what qubits are. Do you want to get a quick?
Yeah. So the classical bit is a binary state. It's an area of your disk where all of the magnet is magnetized either up or down, or it's a switch that has a current in it, or it doesn't have a current in it, or it's some other way of assigning a 1 or a 0 to your device, to your bit. And when you measure it, it either gives you a 1 or a 0 every time. Very predictable, very awesome. And all of our classical computers are built on that fact, right? And so, you've got a 32-bit or a 64-bit computer. That's the number of bits that are addressable by your CPU in order to do your computation. You typically, you've only got a couple of registers at any one time. You don't have to think about that anymore, because your high-level programs and your low-level programs and all of that kind of stuff, they take care of all of those issues. But when it comes right down to it, the computer just takes a 64-bit number and another 64-bit number and performs some operation on it, and then it moves it to memory. And that 64-bit number, that's your processor. Unless you got a 128-bit processor, now you can address a bigger number.
Mm-hmm.
Those are bits. A qubit also is either a 0 or a 1. And every time I measure a qubit, I get either a 0 or a 1. But quantum mechanics will allow that qubit to be in a superposition of 0 and 1 at the same time, which means this. If I measure a qubit that is prepared exactly the same way, and I do it over and over again. I prepare a qubit. Let's say I prepare it so that its spin, which can be either straight up or straight down. I can call this 1, and I can call this 0. That's my bit. But the qubit we think of as being maybe oriented like this as well, which means that if I prepared a zillion of these, all identically, and I measured them individually, every time I measured this, it's either going to be a one or a 0. But if I did it over and over again to that qubit over and over again, prepared exactly the same way every time, and it were actually in this state, I would find that half of the time I measured a 1, and half of the time I measured a 0. And the way to describe that phenomenon we say is, oh, that's behaving like a quantum mechanical device. It's probabilistic. So it's not every time I measure it, I didn't get a 1 every time, and I get a 0 every time. I got 50% of the time it was a 1, and 50% of the time it was a 0. And it turns out that I can contrive my setup to put it in some other state that's like something like this, say. And now maybe 75% of the time when I measure this bad boy, I get a 1. 25% of the time I get a 0, right? And I can put it in any, I can make it so that I can get any state that I want. That is, we call it a superposition. The point to know is that when I make a measurement of it, when I say, well, what state is it in? That requires a measurement. That's the environment going in and saying, it does what we call in quantum mechanics a wave function collapse to either a 1 or a 0. And at that instant, it is a 1 or a 0. But the idea is to put your state in a superposition of 1s and 0s such that as your program evolves things, and I take these qubits and these qubits and I either AND them or them, or I do, operations on them, so forth, so that when I get near the end of my computation, I get to the end and I've got this final thing I need to measure, that when I measure it, the probability that I get the answer I'm looking for is a 1, is 100%, right? That would be the ideal. And even if I only get the right answer, say 95% of the time, which is a possibility because of noise and decoherence, it may only give me but now I only need to run that's the exact same algorithm, 2 times or 3 times, because I know that the error rate is small enough that if I ran it 2-3 times and then I took the answer and I got 1 this time, 1 this time, and a 0 the last time, I'm going to say, well, I'm going to let them vote, and I'm going to say 1 was the answer, not 0 for this qubit. And they have things called quantum error correcting codes that try to do this sort of thing, right? They try to minimize the effect of the environment and say, okay, well, we know that there's going to be some amount of decoherence, some amount of environment leaking in and trying to measure one of my qubits when I'm not ready, and enforcing that state to not be a superposition anymore, be a 1 or a 0, and it'll mess up my computation. Well, I know that some of that's going to happen, so I got to account for that somehow. One way to do that, of course, is, if I can do the computation fast enough and the environment only interacts, and I know it's only going to interact with a couple of qubits, and I get to the end, maybe I run that algorithm 3 times, and I get the same answer twice, and the other one was really close to that answer, and I'm like, that must be the answer. So that's the deal with a qubit, is that it is in a way, it's probabilistic. You've got to make a measurement. And when you make a measurement, it's always going to be a 1 or a 0. But before you make a measurement, it can be in this state that is either a 1, a 0, or some in-between state. Okay. And that's what makes it magical in a way. That's what is the hard part. Because you can't see it, right? You can never see what the state of a qubit is unless you measure it. And once you've measured it, it's not in the superposition state anymore. It's either up or down. So the only way you can really know is that quantum mechanics even works is you have to take what we call an ensemble measurement. You have to take a whole bunch of them and see, oh, you know what? If I prepare my qubit this way and I do it a zillion times and I measure it at the end, each one of those trials, half of the time I get a 1 and half the time it's a 0. I conclude, therefore, that the way I prepared that qubit
is in such a way that half of the time it'll be up, half the time it'll be down. It must be in a superposition of up and down at the same time. And then all of the math works. And that's why we say, quantum mechanics works. Must be true.
I had to pull up the it was a slide. Well, it wasn't a slide, it was actually a definition here I had looked at of not just a computer, but like performing a calculation. Like they were talking about a quantum computer can perform calculation on all four states. And do you want to bring my screen back up so you can give you some context of what he was just actually talking about, right? So if you look right here, it's saying performing. Oh man, that's too big. Let me go back down. It says performing a calculation on two classical bits, which is 0001, 10, and 11. And this goes back to your AND OR gates and stuff that we were talking about earlier. Like, if we needed to and a 00, and a 01, and a 10, and a 11, depending on what gate you want to use, right? And it says two classical bits requires four calculation. A quantum computer can perform on all four states simultaneously. So goes back to what you were saying before, Rick. We can do this all at one time.
That's right.
Right?
And that's the promise of a quantum computer, right? If this didn't happen, if you couldn't put this qubit into a superposition of 1 and 0 at the same time, there would be nothing special about the qubit. This is what makes it cool.
Right. And then it says a quantum computer can perform calculations simultaneously on all four states that scales exponentially. 1,000 qubits would, in some respects, be more powerful than the world's most powerful supercomputer. The promise of quantum computing, however, is not speeding up conventional computer. Rather, it will deliver an exponential advantage for certain classes of problems, such as factoring very large numbers, with a profound implications for cybersecurity, right? And that was under the one for how will quantum computer transform cybersecurity, right?
Exactly. So you can think about, one of the questions is, of course, scalability, and that's one of the things that we're concerned with here with quantum computers and classical computers. How do they scale? And if you had 1,000-bit computer, how many possible states could your system be in? Well, it's 2 to the 1,000. That's a big number.
Mm-hmm.
A big number, especially since 2 to the 10 is about 10 to the third, right? 2 to the 10 is 1,024. If we round it down to 1,000, then 2 to the 10 is 1,000, right? Which is 10 cubed, right? So 2 to the 10, then you have to multiply that. You have to raise that to 100 power in order to get your 1,000 bits. That would be 2 to the 1,000. So that's the same as 1,000 raised to the 100 power.
Right.
Right. So that's let's see, 1,000 raised to the 100 power would be what, a 1 followed by 33 zeros. That's how many states you could do, and you'd have to do them all. You have to do every one of those. You'd have to do 0, 0, 0, 0, 1,000, 999 times 0. You have to run that through your algorithm. Then you have to go back and 0, 0, 0, 0, 1. Run that through your algorithm, and you have to go back and you do that for every possible combination. That's a lot. That takes a long time. If you had a quantum computer, you could do, in theory, a quantum computer with 1,000 qubits. You do it all at the same time. You do it one time.
Right. Now, getting back to that roadmap you was talking about, I actually found a roadmap here. Let me see if I can blow it up some. This is from IBM, and this goes out to 2025. This is what they're saying. And I don't know if you can really see it a lot. Let me see.
Kind of small, but
let me see. How's that better?
Yeah, a little bit better. I see 2025. Yep. I see that.
The scale of in 2025, the prediction is the scale of scale quantum applications with circuit knitting toolbox controlling QKit runtime And
Yeah.
then this year it was bring dynamic circuits to Qkit runtime to unlock more computations. And this is, I guess, what they're predicting here with the qubits. And then you said 1,000 qubits. So here with 2023 Condor
Yeah.
is what their prediction is. I'm not sure what Haran is. I'm not sure what this is. But this is their prediction. I'm not sure if this is true. If they've been on course, I'm not sure. But that was their prediction there.
Right. So, and let's remember a couple of things about this. So, one is this is probably a marketing thing. So they're got to
Right.
get money to do this. So they might be a little optimistic, but still they're going the right direction. I think that's great. It's not just the number of qubits you can address, but it's how long you can keep them coherent. That's going to
Okay.
matter as well. So there are multiple competing things. Remember, you may be able to generate something with 1,000,000 qubits, but if it only lasts for one step in your computation, and then it all decoheres to heck, it's not going to do you any good. So you have multiple things to solve, but there are more people working on it now than there were in 1999 when I finished my dissertation. So
So with that being said, let's talk about that. Would you recommend, looking back over it now, would you recommend someone going into that area of research? Um, as an engineer maybe coming up, because we have computer engineering, electrical engineering. I never really hear people say I want to go into quantum computing or do quantum engineering. Is that would you recommend that as knowing what you know now, and then just looking at the job market, would that be something you would recommend? No, about don't be biased either.
so maybe to preface this, let me say that when I finished my degree, I applied for over 100 faculty positions to continue on to this in this vein, right? To continue doing research in this area. And I didn't get any. And most of the time it's because the departments didn't understand it. And they said, you wouldn't even have a colleague here you could bounce ideas off of because it's so new. Nobody worked in that area here. You'd be an island. And it's hard for us to think about that. But, things have changed a little bit now over the last 25 years. If you're interested in it, I would think that it's still the ground floor. So if you want to get in on the ground floor of something, and if you're early in your career, and this is really interesting to you, this could be a lifelong career for you. And you could work your whole life in quantum computation, your whole career, your whole professional life. But know that it is, right now it's a little less engineering and it's a whole lot of like physics and research. And, it's like research engineering. So you have to like that stuff. And it also means that, it's not like if you don't like your job that you're going to go down the street and get another job being
Right.
a Linux administrator.
Right.
There's just not that many around. You've got a handful of places to go. A lot of them are at research institutions, or they're at some of these big computing places that we've talked about today that have a research arm that are able to support. But for some people, that's exciting. And yeah, sure. I mean, when I finished my master's degree, which was in superconducting magnet technology, by the way, they wanted me to go on in that. And they're trying to build the International Thermonuclear Experimental Reactor at the time. The thought was, we can build a fusion reactor that'll be commercially viable in 25 years. Well, it's been 30 years now, and I think they're still about 25 years away. So if you're okay with not knowing the certainty of the future and maybe spending a long time doing basic research and stuff, that's great. Then it would be an exciting field for sure. There's so much to learn. There's so much to do, so much to discover.
And I went on Indeed and looked up just to see how many jobs was out there. I found like 3,330 jobs. Just I want to research like an associate quantum physicist, at who is this Northrop that NG Northrop Grumman, cybersecurity apprentice, senior cybersecurity. And I'm gonna uh, count these are research, but it's interesting how people have paired Java, JavaScript, CI/CD, quantum computing required, like quantum, quantinium, I guess quantinium, director of information security. Of course, that's over at Honeywell.
Yeah.
Right, over at Honeywell, and it's just interesting to see the positions and what people are looking for, and how what companies really are looking for quantum computer people, like sales development representative, like experience a strong interest in quantum or emerging your sales development. I don't know, Rick, like the requirement there is interesting, right? Where do you find someone with sales and quantum? Where is it
How long's that been open? I mean, that could have
at?
a hard time filling that one. But I think that there are probably a lot of companies out there. The well established. I think you're going to have three. You're going to find three classes of companies. One is the big companies that can afford to dump money into a research program, like
Mhm.
your Googles and your Honeywells and your Northrop Grummans and that kind of thing. The really bigs, they're going to have that. Then you're going to have a bunch of startup companies, people that've got some ideas and maybe got some seed money, or maybe they got an SBIR in order to do some research, something or like that, or an STTR. That I've seen lots of those that are building some little device that's going to help quantum computing in some way. And then you're going to have this middle tier of companies that are, in the middle, and they're the technologies that they're working on, develop, support, service, whatever, may not be directly quantum related, but they're worried. They hear quantum all the time. They're worried they're going to be left behind if they don't have somebody that's looking out for that, that's keeping an eye on it, that's going to figure out how it's going to impact them and their business. And so, who knows? Some of these positions may be that. Some of the sales positions, we just want somebody that's going to keep an eye on quantum and make sure that we understand it when it becomes really important for us. But I think, if you're looking for a career in this, I'd be looking at the bigs. I'd be looking to go join a team, learn from what has been done before, and join a team that's doing research in quantum computation. That's where I'd go.
So the IBMs, the Honeywells, the bigger companies.
Yeah. Yeah.
Got you. Got you. Now, with that being said, if you had a chance to say you retired, right? Would you go back into doing more research on it, or will you just be retired? Is the passion and love still there?
I love teaching. So if I found a position where I didn't have to work too hard for the research dollars, I might do it.
I got you. I got you. We also opened up the chat. We also dropped in the chat. I know you got a. I know we got you about 15 more minutes, right?
Yeah. Yeah. I'll stick around. You bet.
Yeah. We dropped in the chat the link if anybody wanted to come up and ask Mr. Dr. Rick Nelson in any questions and so forth. Please feel free. We're gonna bring Dee back up in case Dee got any questions that she wanted to ask. I know I probably monopolized most of the conversation here, but I'll let Dee do her thing and ask questions.
Actually, I actually don't have any questions. Things that when you were speaking, I was looking them up online and I was sharing in the chat. So I was clear about what's going on. But I want to thank you. It was a great conversation. I
Oh,
learned something new today. I know years ago we were talking about quantum computing and we went to a few local events here in Tampa, but so much has happened. So it was a refresher to know the intricacies about what's going on in quantum, how it relates, what it's tied to. So I thank you for that.
Oh,
Yeah, I did a talk. I did actually did a talk on quantum computing. As like where people were looking for engineers, and I did that at Lisa, at their. Yep, I did that at Lisa's because it had started coming up that more companies like your IBMs, your Googles, your so forth were looking for people to help, not necessarily build, but help deploy these applications and create CI/CD pipelines and so forth.
right. Well, I think one of the interesting things about quantum computation for the general, say, computer science community is that it's you're probably going to have to be a little bit of a unicorn that way. It's not you're not going to program a quantum computer the way you program classical computer. You're not going to even think about architecture the same way. You're not going to think about how the processes go the same way, and some of the problems are unique. Like I said, the decoherence problem, the probabilistic interesting thing at the end, where you make a measurement and the whole state collapses to ones and zeros, just like it would in a classical system. You don't know the difference. Usually, I got a bunch of ones and zeros. Is that classical or quantum mechanical? Well, it's quantum mechanical and it came from a quantum mechanical system. But the output we've got to live with in the real world, and it's going to be ones and zeros, right? It's going to be
Mm.
classical output in the end. And some of the ways, the ways that we think about computing are different and need to be different for a quantum computer. But there's room for people that are interested, people that are looking for a hybrid. We're still going to need classical computers for as long as I can see. We're not getting rid of those. In fact, you probably use your classical computer right along with your quantum computer. Right now, you run an experiment on your quantum computer, and then you write up the results on your classical computer. No one's running Word on their quantum computer, and they probably never will because this is not,
It's not feasible.
and the classical computer is better. It's just plain better, easier, cheaper, in so many ways in order to solve that problem. I can touch the keys of my computer and I don't have to worry about the heat from my fingers destroying the state, and changing the words on my page to gobbledygook.
Hmm.
Um, but you have to be adventurous a little bit, and it'll be a little more physicsy and a little more researchy at first if you decide to go that way instead of you know um, how do I install the most recent version of this VMware product or something. It's going to be a lot more basic than that. So
I got you. We did have engineering cannabis up, and I'm not sure what happened to.
He had a little one on his lap, so I'm pretty sure he had to go deal with that little one, and it
Okay.
got a little noisy. So he's back up. Let's see.
Okay, here you go. We'll bring engineering cannabis up. Hey, engineering cannabis, how you doing this morning or afternoon? And you're
You're
on
on
mute, by
mute.
the way.
I'm great. How are you doing?
I'm all right.
All right. Thanks, Dr. Richard, for coming in. I'm enjoying the whole concept of quantum computing.
awesome.
I'm trying to get into it. Basically, I do numerical analysis and machine learning, especially with mathematical models. And one of the biggest issues I'm having is basically every professor and everybody keeps telling me that you cannot model human behavior. That's one thing you cannot because it's too dynamic. And
Mm.
everybody keeps telling me that. So one of the biggest problems I'm involved with is trying to model the health of a heart, the heart system of a human being,
Uh-huh.
and that whole system alone, the variables accompanying that situation is huge.
Sure.
You're talking about not only you're talking about, I always model it based on internal and external. Not only external factors dealing with not only stress levels, exercise, all that, then internal metabolic systems, all this basically trying to just model the heart.
Sure.
And not only that, also again location, and then you have to do it based on time or space, all that.
Yep.
And right now, they're trying to do it with the modern, with again machine learning and all that. It keeps breaking, it doesn't work. But how do you see that going in terms of quantum computing, in terms of that, trying to model the most dynamic system in the world, the human? How do you think the quantum computer could that be even handled with a quantum computer?
Sure. So I the whole idea of the heart is not human psyche. So I have faith that you could consider it a mechanical system.
Yes.
It's got height, size, weight, dimensions, pressure. It's a physical thing, and you can model just about everything on there.
Yeah.
What the quantum computer would allow you to do is to certain questions that you would ask that you can't model in real time with the classical computer. That would be where you would look to a quantum computer to say, can I, if I need to run multiple simulations to get an answer, can I, and it takes too long on my classical computer, can I do that? Quantum computer, that's where it helps. This is the whole thing. The modeling is going to be the same. You're going to model it the same way. That whatever variables you would have,
same equations, same variable.
all the equations, all the dynamic equations, state equations, equations, all of that is exactly the same. But if you find that I've got to run the model, say you had to run the model 1 million times, you get a probabilistic answer at 57% of the time. If XYZ occurs, the guy's going to have a heart attack by in the next year, for example, something like that.
Yeah.
If you find that simulation would take a lot longer on your even if, and I would go to, you should keep in mind that classical supercomputer, or classical, maybe you got 256 addressable bits on your classical supercomputer, right?
Mm-hmm.
Compare that. If you can't run the model there, then you could say, well, maybe I have a chance at supercomputer helping because you can run 1 million of those simulations all at once. So this is the power of the quantum computer, is to be able to run multiple simulations on a large addressable space at the same time. That's where the power comes from.
And in terms of the quantum computing, do you think new algorithms will be created, or will have to be, again, you said new languages have to be created to address quantum computing. So will we, again, math is math. We have to build on it. But do you think new algorithms will basically be created from the event of the advanced quantum computing?
I think so. So, there are certain things that we do in computing all of the time, like we mentioned some, like an XOR gate, an OR gate, an AND gate. These are typical gates. And one of the first questions that we came up with, right, is, first of all, can a quantum computer simulate a classical computer? Right? Can we use it to do what a classical computer? Can we use it to compute 2 times 3? Right? And so, and how would you do that on a classical computer? You'd call up 2, you put it on the address bus, you'll get the address, you put it on the data bus, you call up 3, do the same thing, put it on the other data bus, you perform, the steps, the and, or, and not gates that you would need in order to perform the computation. And then that would appear in one of the address buses, and then you would write that with, to another address, and then you stored it, and that is the answer. One of the questions we have is, can we do that with a quantum computer? So the answer is yes. And the next question is, well, with all of the gates that we normally use for classical computer, what do they do in a quantum sense? Do they do the exact same thing? Do they have any extra coolness to them? And so that's one of the next things they started to do. And this is in the 90s, right? They started to look at what these gates do. But I don't think we've fully taken advantage of all of the quantumness, if you will, of a qubit yet. And so people have started to come up with different combinations of gates that don't have a perfect analog in the classical sense, in that they don't give you the result that you normally would want. Now, there are some theories out there, theorems actually, that show that you can reduce any sequence of gates after you make, and then you make a measurement, which collapses that state to a classical ones and zeros, that
Mhm.
you can replicate and you can substitute if you can find the right combination of classical gates. You can build up any combination, any algorithm that you want. So the questions now become, how do I do that efficiently? How do I write a language that will take advantage of those efficiencies? How do I implement that in the physical hardware that I have and uses a quantum computer? All of those are things they're still working on. And so those are the areas of research that we were talking about earlier that would be cool to explore. And that's where I think there's new languages. I think you're going to see new languages that are going to come out. And they're going to be, at first, very specific to the way that their particular quantum computer is set up physically. One that uses, they're all equivalent in terms of quantum power of computation, but how do I make my quantum computer compute something when it's a lattice of quantum dots, versus how do I do it if it's a photonics bed that has a bunch of light emitting things and mirrors and so forth. The implementation may be different, so you may have different languages that would address those. So right now they're working on, they've been working on two main ideas on how to describe what we mean even by an algorithm. One of the gate concept that I've been talking about, right? But there are other ways to describe what we mean by an algorithm in sense. So
one more question, and this is dealing with the financial market, especially with, again, predictive algorithms like the ones with GDP that try to basically get a sense of GDP, which I've not seen because it's a huge, massive problem trying to compute GDP, predictive algorithms. In terms of GDP, in terms of financial markets, with banks, I'm thinking banks should be investing in quantum computing in order to have that the advantage to compute or predict how the GDP of an economy can go through. So do you think banks investing in quantum computing right now will give them the edge in order to basically get knowledge of the financial markets?
Rick, before you answer that, cannabis engineering cannabis, what would define a bank? Listen,
No,
hold on. Here's why I say. Here's why I asked that. Because when you say bank, I'm thinking J.P. Chase Morgan. I am thinking
America is a bank. Isn't America a bank on its own?
I'm thinking Charles Schwab, right? Because they all have. You can get a checking account at those places. When we normally think of banks, we normally think of the Wells Fargo, Bank of America, right? But I wouldn't expect for them, me personally, to go and have a quantum computer. They will probably leverage a quantum computer, but I would expect a JP Chase Morgan or a Charles Schwab to have one.
Let me rephrase it.
That's my personal
A
thought.
financial institution. Is that better?
So there are several ways to answer your question because there's several facets to it. I think one of them is I don't know what traditional banks would care about GDP as much as the Federal Reserve or the United States Department of Commerce or State or something like that would be probably more interested in GDP, whereas the banks are going to be and are investing in the big banks are investing in quantum computation because of the cryptography breaking ability, and they need to understand that and get ahead of it so that the financial transactions are safe. And that's the big drive for, I think, the banks. But now if we're talking about like JP Morgan Chase, somebody that's got interest in the financial markets of Wall Street or the NASDAQ, or something like that. Now we're talking about, a model that I need to run faster than the financial markets change.
Yes.
So the financial markets, they typically close at 4 o'clock. At least Wall Street closes at 4 and opens the next day at 9. So, or 10. So I've got the time from when it closes to the time it opens again to run, the best model with the most complex model that I can to find out whether I should invest and at what price to buy, all of those stocks that are in my portfolio, or whatever. And that's a hard to do. That's a big and when it comes right down to it, remember, a computation is a model execution that's been reduced to an algorithm. So that's all I'm trying to do is execute a more fancy, more
Statistical
complex
guess.
algorithm with my and if parallelism helps, if qubits help, if maximum entanglement helps, because I can run simulations all at the same time over a bunch of different scenarios at the same time to get one answer. Because when you make a measurement at the end of a computation, you always get just one answer, no matter what program you're running. You get an answer, and that's it. If you want to get try a different set of stuff, you got to run it again with different inputs. But even with a quantum computer, you're going to get one answer at the end. If that answer takes longer to get than the time you've got to run it, then you should be thinking, is there a way to parallelize this? Is there a way to use, quantum computation's inherent advantages to speed this up? And if the answer is, well, if I can run multiple scenarios at the same time, then the answer may be yes. And if the answer is yes, then the next question is, okay, now how? How am I going to write an algorithm that'll take advantage of the quantum computing's architecture, hardware, and that kind of stuff in order to get that answer? How many qubits would I need? And that kind of stuff. So right now they got fancy supercomputers that do this every day. They run financial models every day. We got to be able to do better than that with a quantum computer. Otherwise, they wouldn't build one and they won't buy one at Wall Street. But I think you're onto something there.
So because I'm more in the verse of, because again I understand numerical analysis, machine learning, and I'm also trying to understand quantum computing in terms. What are your suggestions in terms of someone who wants to get introduced into the area of quantum computing, and in order to understand, again, take advantage of it and understand how to apply the mathematical knowledge, especially to quantum computing? And again, I'm not a physicist. I have no interest in physics, but I do love quantum computing in order to understand the algorithms and numerical analysis and quantitative analysis.
Yeah.
And understand that.
Well, so there's good news and bad news here, right? If you really want to understand quantum computing at the basic level, then you would have to have some basic understanding of quantum mechanics. There's no way around it. On the other hand, it's possible to make contributions in this field without really understanding it in terms of, like, how do I build better hardware? How do I access, the computer? If I look at only the algorithm stuff, you can understand what an algorithm's input and output are without understanding how the quantum stuff works in the end necessarily. You just be open to some wacky quantumness, about that. But you learn the basic rules, and then you're off, designing algorithms. And then I would start with, if I were you, I would just Google. I would go to IBM. Go to the IBM site. They've got all kinds of videos and tutorials there that would teach somebody from the ground up, in layman's terms, what a quantum computer is, how it works at a basic level, and that'd be where I'd start. And then consider taking a course in it from a computer science department, not from a physics department. Unless you really want to get into bras and kets, Heisenberg, and different.
No, I'm good.
But they're all cool. I mean, I love.
Yeah, they are good. No, I understand how cool it is, but I'm dealing with my own mathematical equations and all that. But I want to learn more, so I'll start looking into it. And thank you again for the advice. And
yeah, you bet.
Tam, thanks again.
You're welcome. And I think on the IBM side, you can actually deploy a quantum, like on here it says, free cloud simulators, access to 7-qubit, 5-qubit QPUs, build circuits in IBM Quantum Composer, IBM Quantum Lab, and QuizKit, and execute workloads more efficiently. And that's just on the open plan, and they got different plans that you can go play with. Trust me, when you sign up, they're gonna be reaching out to you and asking a whole bunch of questions and so forth. It was a big push probably like 3 years ago for people to come on board and just see what it is. What is this quantum computer? What can it do? They were hosting seminars. You can go back on YouTube and look at some of the videos that they had where they were explaining quantum computing to like a 5-year-old, and what does it do and what is the significance of it. And so there's a whole stream that this has been going on forever. I think it's just one, like Rick said, it's one of those things now where you're really still at the ground floor of what it could be, but it also, you have to have the mental capacity to say what's the long term gain here. What am I going to be able to do for the next 15 years, 10 years, 15 years, if I decide to go this route?
And do you think the cloud technology and the quantum computing, how do you think that will go in hand? Is it going to be a symbiotic relationship, or do you think one has to go? How do you think that will happen again with quantum computing and cloud computing?
Cloud will come. Cloud is already on us. We're already
Mm.
at the cloud. Cloud is way earlier because it's based on classical computation. I think though probably the most likely route I see going here is that just like when classical computers started, you had people like IBM that built, UNIVAC. You've got these big
Mm.
computers that only research institutes can access at first. And it wasn't until about 1984 that the layman could go to the store and buy something they could put on their desktop, right? And it became the
Mhm.
PC, right? And
Mhm.
Apple had their Apple IIc, in about, I don't know, 1980, 1981, somewhere around in there. And that was the beginning of people being able to do that. I think similar is gonna happen here, and probably because the cloud is so prevalent, and you've got all kinds of people that want to get into new technology, is that these these quantum computers that will only be affordable and built by the Googles and the Northrop Grummons and the IBMs of the world will be accessible to normal people at first through the cloud. So you use
Mm.
a classical computation thing to go and then
Mm.
program your quantum computer and let it run the simulation, and then you get the answer
That's
back.
a lie.
You're able to do it from your desktop unit at some point, until at some point, if it ever happens, that you're able to go and buy your desktop unit.
No, that's good. Thank you.
And it's funny that you mentioned this, because this goes back into the other show. And Rick, I'm not sure if you're familiar with family offices and what they do. Like most of the time, and this is just from being in the other group that we're a part of, the Black Card group. One of the big things there, like most family offices don't like to run. They don't like to use their money for risk. They like to use their money for research and guaranteed results. I could even see like a family office being interested in quantum, because it's a research thing. They will pay for the research of it, right? So like if you, just theoretically speaking, created a fund that goes off and starts doing the research of quantum on something, like your idea here on the heart, right? That I could see a family office funding that, to do that type of research, where you'll have, some support, financial support, because again, from what I know from researchers, they're mostly starving. That's what I know from researchers. Rick, you can correct me if I'm wrong, but most researchers are starving, right?
That's right, and that's why that's why when you ask me if I'm retired, I go back to this. I'm like, well, maybe.
could could not possibly,
I
maybe,
am used to a certain lifestyle.
right?
Nah, that's not for me either. But I love the whole system. I love the whole premise. I love the possibilities. So I'm just trying to use what currently is on state and trying to envision what might happen with the use of quantum computing.
Right. But that would be where I could see that, yeah, see right here, family offices warm up to quantum computing. I kind of figured that, because it's one of those things that, doing research and so forth, they said a race for quantum computing advantage warms up. Family offices are frequent backers to the sector, expected to be worth 65 billion by 2030. And again, like I said, I could totally see something like that. So,
Mhm.
there may be hope out there if you did want to go this route, engineering cannabis, like to do some research on that. But it wouldn't come. I don't think it would come from your traditional way. You would probably have to create a fund that is looking to do this type of research and have researchers in your fund and what you want your outcome to be. Of course, you got to get somebody to run the fund and then go talk to these family offices and present what you're trying to do and what you're trying to accomplish, and probably pair it with some institute, some educational institute, and maybe even somebody who wants to do their doctorate with this and pull that together to do something like that. That I could totally see that.
I see all the bells in your head ringing like that. I see all the bells ringing in your head.
I'm just saying.
Okay,
I'm just saying.
I'm listening. I'm listening.
There it is. There's your model. There's your idea. Now you have to flush out that idea and turn it into a fund. And then once you start creating the business case and so forth, then you have to find someone to help you go and get that information, which it's possible. That's really possible. There you go.
Thanks.
You're
No,
welcome.
thank you. Again, thank you everybody for a wonderful conversation. I really learned a lot today.
You're welcome.
Thank you.
Thank you for coming
Thank
up
you
and
for
answering
coming
your
up.
questions.
And Rick, we thank you. We know we ran over your time here. We want to make sure that you get your Saturday back. And
Nowhere else I'd rather be than with you fine people. So
oh, look at there. Look, he's so sweet. Oh.
Look at you.
All right.
I
anything-
apologize. I did not proudly wear my Women Linux T-shirt.
It's okay. It's all right. You told us to
You got a collar. I gotta get me one of them. That's what
you got to talk to Dee. She's the one that's supposed to be
Get you
doing
one
all
with
the
the collar.
collars.
You gotta hook
We can
me
get
up.
you purple. We can get you navy. We can get you gray.
Oh, I'm liking all of that. That sounds awesome. Let's do it.
Yeah.
We can get you something.
And Rick, I thank you for coming out and being a supporter of Women in Linux and all the endeavors we've gone on, even inside expansion and outside expansion. We would love to continue to do work together as well too. And we appreciate your time for just even going down memory lane for you, really, for and bringing that back up. Did you want to give any spiel about expansion while you're here? Did you want to talk about any job openings you all have, or what you're
We're
looking?
always looking for good people at Expansia. We are, IT services firm, cloud transformation, and we do some additive manufacturing as well in there. We're all about process. Most of the positions are, we do support for the Department of Defense. So if that scares you off, then don't get scared off because it's pretty cool. But we have positions. You can go to expansiagroup.com. Find positions there. They're listed there now. And we're a very patriotic group. We love supporting the Department of Defense, our country, and like to give back to the communities that we serve in. We just completed, I don't know if you knew this, Tamika, but was it last week? A weekend before last weekend, we repainted the whole inside and redid the whole playground for a house called Abba House in Georgia. That takes in it's in is it in Perry, I think, Georgia, or Warner Robins area. Anyway, they it's all helps women get back on their feet if they've experienced like sexual abuse or they've been human trafficking, or if they are addicted and that kind of stuff. It's a 15-month program that teaches women skills they need. Also, their kids can live there as well. They're all part of the program. Teach them how to be a family and to be able to survive. Give them work skills, that kind of thing, so that when they're done, they're not dependent on the state. They can make their living and support their families and that kind of stuff without any of the kind of traditional vices that we have. It really is freeing. It was awesome. And we were proud to partner with them, volunteer, help them bring their facility up to snuff. So we're about giving back to the community as well. But as a company, we're always looking for good people. Love to have you. Tamika is a rock star at Expansia. We still turn to her.
Thank you. And we appreciate you coming out. Did you want to leave
Thank
anything?
you. Thank you. Thank you for coming out. It was good to see your face. It's been forever. And I hope to see you guys back soon.
Awesome.
You're welcome back anytime.
You guys want me? I'll come back.
Yeah, you're welcome back anytime. Just let me know when you want to come back, what you want to talk about, and we'll hook it up.
Awesome. Sounds great.
We appreciate you.
You bet. Thank you. Talk to you later.
Thank you.
Well, there you have it. You've heard of, even from engineering cannabis, you heard some use cases, you heard where we're at, what we're looking at. I encourage you really to actually look at the field a little more, just so you're aware of when you see these things that come out, especially there's been a lot of conversation around satellites on this. There's been a lot of conversation around cybersecurity. And this goes back to what I say before, when people say they're interested in cybersecurity, what does that actually mean, right? What does that actually mean? Is that from a research perspective? Is that from a penetration testing perspective? Is that from a red team, blue team? There's so many different aspects when we talk about cybersecurity and just tech in general. So that that you have, that's just another another aspect of tech that could be, you could go and do research and be on a research team. I also see that being played out on quantum and crypto, right? So you just never know what that looks like for people, what companies are looking for in terms of research. Yeah, currency faces a quantum computing problem. That's been a talk for forever. What does that look like right here? This came out last year. I actually spoke on this article here, about quantum, cryptocurrency faces a quantum computing problem, right? I talked about that, and there's been a lot of research going into that. Right here, this just came out March. This is from CoinDesk: Quantum Computers versus Crypto Mining, Separating Facts. You're going to see these conversations come up, and they're like, Rick was saying that they just want people that may just be in the know about what's going on, where people are at, what they're doing, and so forth, right? So again, this is one of those areas that you could potentially just be doing research in, right? You just having your ear to the ground with a company. That if you work at an IBM, if you're working at a Google or Amazon, they in fact they just somebody just bought a team. Let me pull this. I had some stuff up earlier. Let me go to my notes, and I can pull this up because I was just interested in it. So right here, here's where I got it from. Right here, my on my search, because I always want to be ahead of the curve. Let me blow this up some here. All right, yeah, War Fund joins 128 million bet that quantum can deliver climate breakthroughs. And that was 19 hours ago. IBM holds a new error mitigation technique will help it get to quantum advantage. This is what Rick was talking about earlier. UK Oxford Quantum Circuit snaps up 47 million in a Series A for QAAS, quantum as a service, right? Quantum as a service, right? Amazon extends its quantum efforts with focusing on networking. D-Wave launches a first prototype of its next-gen annealing quantum computer. Class Q raises additional funding for its quantum algorithm design tools. Another conversation when we were talking about algorithms, right? So again, this is all this all the way up to here was May 10th that they reported on, and then this is the 2018, and this is 2021. But again, you can see where people are looking for and doing work in quantum and what that looks like. So if you did want someone did want to go into and do research or go back and do their PhD in it or something of that nature, you have some ideas and some options. And also, again, like I said, I showed you about the fund. The family offices are warm to having the research behind it and the fund, like especially if you can predict in time markets and look into predicting in time markets and want to throw research into that and how I can help keep my billions, my millions, billions. Yeah, I'll help you find. Yeah, go do that. You may not work for it may not work for me now, but it may work for my portfolio in the future with my kids or my grandkids, right? So why not? Right. So just thoughts on that.
Great conversation. Thanks,
Cool.
Engineering Cannabis, for coming up. I know you are bursting at the seams with your questions. You were like, "Are you guys going to share the link?" I'm definitely going to share the link.
Yeah.
Again, thanks. I like somebody called him Dr. Rick. Thanks, Dr. Rick, for coming up and sharing with us. It was always a pleasure.
Right.
We have nobody else backstage.
Nope. Nobody else backstage. We're
No.
gonna get into tech stocks and jobs. Be ready for that one because that's gonna be a doozy. Just letting you know how we do. Oh, we'll probably have more conversation on that. I don't know. We might drop the link on that because it's in the evening and we can actually get into discussion on it. But we'll look for you all at what 30 minutes.
In 30 minutes. Yep.
30 minutes. All right. All right. We'll see y'all then. Thank you for coming out. Again, thank you for the super chats and thank you for being a part of the group. And don't forget to hit the like button. Don't forget to hit the subscribe button. Don't forget to hit the notification. And don't forget, we also have memberships. Right. Don't forget to become a member. We're actually gonna I'm trying to do some stuff this weekend. If D is ready. D, you ready?
She's not going to do nothing this weekend. It's a full plate.
What
Don't
the-
let her hype you up.
Yeah, I am. Believe the hype. Look, I'm a quantum computer over here. All right,
I
y'all. Y'all
know.
have
Cyborg. I keep trying to tell people they don't believe me, and I'm like, let me just keep my secrets to myself. She's a drunk. Like she's a AI bot computer.
Speaking of AI bot, now that you mention it, let's hold on before you go. I was looking at the article in this MIT technology review. I get these and I go through them, right? And
I'm glad you finally opened the mail.
you glad I went and got it. All right, so hold on. It's called Gender Bending Filters Can Revolutionize to People Questioning Their Identity. All right. And so they got in here, and I'll put this one up if you can see. All right. Where the first one is the guy, and then the second one is him morphed into a woman.
I saw that they would do those with celebrity guys, like what they would look like as a woman.
Mm-hmm.
But I mean, shoot. Hey.
But again, this reminds me of the ultimate catfish, right? So now technology is gonna help people catfish. Is how I look at it. That's just how I look at it. But again, I thought it was interesting when we started talking about morphing people and what you could look like and so forth. Just my little one off there. Nothing to do with what we were talking about, but just my one off. That's it.
Is it?
Mm.
Is it? And then they have that one that turns the women into guys. On my cousin had it, and it gave me like this goatee and stuff. We fell out like it tickled me so hard. I cried. It was so funny.
I need to see that.
I got the picture in my phone. It was hilarious.
Were you cute?
I was handsome. I looked like my dad. I was handsome. And we were in Macy's, and I yelled, we were tickled. We were in the dressing room at Macy's. We were so tickled.
You can be anybody you want to be these days. Anybody you want to be. That anybody you want to be.
You definitely can. You always could be.
Will they? What Code Adam? You say will they get it right for sister, brother, twin? Oh no. Who knows? All right, we'll see y'all in a little bit. Be ready.
Thanks for coming. See you in a minute.